Welcome to AP Biology. I'd like to talk about emergent properties of water today. Emergent properties mean something that's kind of really cool that you didn't really predict would happen based on what you started with. So for example, water is made out of hydrogen and oxygen, and they're both gases, right? And they're flammable. And then you put them together and you get this molecule that's a liquid at room temperature that is not flammable. So there are other emergent properties of water that are even just make water cooler than pretty much every other substance out there. And most of these emergent properties for water have to do with hydrogen bonding. So quick review here. This is a covalent bond between the oxygen and the hydrogen. So that's covalent. But this, between the partially positive hydrogen and the partially negative oxygen, that's a hydrogen bond. It's a weak bond, but all of those hydrogen bonds together can do a lot. So, water has four emergent properties that I want you to know. The first one is that it's cohesive and adhesive. So, cohesive means water tends to stick to itself. And so you can see that here in the surface tension. If you've ever filled a cup up a little bit higher than you should have, maybe, it like sort of bumps up over the top. You would think gravity would be pulling it down, and it is, but the water molecules are attracted to the other water molecules, and that helps hold it in. Kind of cool, right? And then you can also see that's what happens when you have water form a ball, like it's doing here. The water is really attracted to itself, so it's forming this kind of cool little ball there. And you can see an insect crawling across or walking across the surface of water again because it's almost like a little skin on top of the water. It's this extra force where water is more attracted to itself instead of going like up the um, the little critter's legs. Okay, another thing is that water is adhesive, which means that it's attracted to other polar things. So you can see that in capillary action right down here. So the thinner the tube, the further water will creep. You can see it with just the meniscus here. Like, do you see how it sort of forms this curve? It's because the water's sort of creeping up the sides, and the thinner it is, the more it creeps. So we have really, really, really thin tubes in the xylem of trees, and those little tubes are what water sort of is attracted to and sort of crawling up. And then another thing that happens is water leaves when it evaporates, when transpiration happens, right? And each of those water molecules that comes away is pulling a water molecule from behind. And so that one kind of pulls the one behind it, which pulls the one behind it, and that helps to draw water out of the ground into the trees. The next idea is that water has the ability to moderate temperature. So if you live near the coast, your temperature is more moderate. You don't get quite as cold and you don't get quite as hot as you do inland. That's important for anybody who lives near the coast. So I'm lucky enough to live not too terribly far from the coast. Whereas if you live like in the center of the country, you tend to get a lot hotter summers and a lot colder winters. It's also important for creatures that live in water. So here is a really bad picture of a lake, and there are fish that live in here, right? And so the temperature outside is going to fluctuate a lot more than the temperature in the water itself. So if you do live near the coast, you might notice that in the spring, it takes a long time for the ocean to warm up. Um, but then once it's warm, it also in the fall, it takes a while for it to cool down. So water really takes a lot of energy to heat up and a lot of energy to cool down. So it moderates the temperature of any organism that lives in it or near it. Water has a very high specific heat, so it takes a lot of heat for water to change temperature. So that's important, especially for phase changes. So for example, if you're here on a hot day and you are very hot, some water will evaporate. And so it's the hottest water, it's the waters that are moving the fastest that are going to evaporate. The way I think of it is to change phase from liquid, the sweat on your body, to gas. It takes energy to change that phase change, right? To go from liquid to gas, and so that energy is sort of taken out by evaporation. It's really like the most energetic molecules that are going to evaporate first, and the same thing with other phase changes, and just with temperature changes in general. In order to make water heat up, you've got to break up all those hydrogen bonds. and all together they're a lot of energy. So it takes a lot of energy to heat water up, takes a lot of energy to cool it down. So if you do live near the ocean, you might want to go swimming. It's a nice hot day in June and you're like, yay, let's go swimming. And you'll notice the air is a lot hotter than the ocean. There's a lot of water in it, first of all, but also the hydrogen bonds just take so much energy to heat up that it does take, really, it's not really nice to swim around here until August. It takes a couple months to really heat up that water because of all those hydrogen bonds. Okay, specific heat is the amount of heat, you don't need to memorize this, but it's the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. All it means is it takes a lot of energy to heat up water, and a lot of energy is released to cool down water. So much of the heat is used to disrupt the hydrogen bonds, these, when you're heating up water, before the water molecules can begin to move faster. Or if the temperature drops, it's the additional energy that hydrogen bonds will like release when they form. Okay, water has a high heat of vaporization, sort of the same thing. Takes a lot of energy for it to change from liquid to gas, and so that's the heat of vaporization. Because it takes a lot of energy to change from liquid to gas, you cool down when the water does that. What's really happening, I guess, is each individual molecule, the ones that are moving the fastest are the ones that become vapor, but it takes a lot of energy to do that, and so you cool down. Yay. Evaporative cooling means as water evaporates, the surface of the water cools, which is why you cool down when you sweat. So the most energetic molecules leave and the slowest ones are left behind, the cooler ones. So this is also true for trees. During transpiration, they also cool themselves off this way. And then finally, 3. So another one is expansion on freezing. So the weirdest thing happens. Usually solids are small, and that same amount of solid, when it warms up, becomes a liquid, and it takes up more space usually. And then to become a gas, it takes up even more space. That's not how water works. It's the weirdest thing. When water freezes, it's actually lighter because of the way the hydrogen bonds end up forming this sort of rigid lattice. And so they end up expanding when they freeze. Coldest water is most dense. I think it's like 4 degrees Celsius or so. But the key here is that ice floats. So it expands when it freezes. So why does that matter? Because if water, when it freezes, was like every other pretty much material, when it would freeze, it would get more dense and it would sink. And so what you'd have happening in a lake is the water up here would get cooled down from the atmosphere as things got cold. It would freeze and then it would sink. And then it would freeze up here and it would sink, and then it would freeze and sink. And so what you would end up having, what would happen is that the whole lake would freeze over and all the cute little animals and the plants would die. So it's nice that ice floats because it might have been tricky for life to evolve in um, lakes that would freeze solid. Um, or at least maybe that happened where it was warmer, but it's harder to live. When water becomes ice, it there's very few organisms that can withstand getting frozen. Okay, finally, versatility as a solvent. Water does not dissolve everything, but it does dissolve lots of stuff. So water is a good solvent or dissolver with a whole bunch of things, ions and anything polar like carbohydrates, not lipids, carbohydrates, proteins, nucleic acids. So water dissolves a lot of stuff, not lipids, but pretty much everything else. And that's it.